Okay, can I call everyone back to the fold, to the comfort of these lovely seats here, so that we can start the next session, which is Dave Wecker again, but now he's going to give us a tutorial on the BQIT, or liquid. BQIT is a nice name, I think. Yeah, I'll stick with that one. So he's going to give us a tutorial on that, followed by questions. So without further ado, let's begin with Dave Wecker.
And actually, that's not as funny as it sounds, because the legal department wouldn't let me call it liquid, because you can't copyright that internationally. There's all sorts of places that it's a problem. So calling it BQIT is actually the official name, according to our legal department. So, and I think I mentioned this morning, but there's no need for you to sit here and program with me. You're welcome to. And any of you who have done the installation of the software beforehand, you'll be able to keep up with whatever I do, but there's no need. You can just watch this. Also, I'll show you at the end on the website, there's a video of this entire tutorial. So you can always go home at your leisure, sit there. It takes the same amount of time, and you can run it on your machine. It's also worth mentioning, in case it got missed along the way, that this runs on Windows, OS X, and Linux. So there's no need for you to have to put a VM on your machine and try to run this if you're running a different piece of hardware. And what I'm going to do is not do a talk about liquid, but we're going to talk about here's how you use it. So this is going to be installation, how to run it, how to actually do the built-in samples, how to write your own code. We're actually going to go through, actually program the system, write our own code, and then do some quantum chemistry with it, do Shor, dot. So it'll be enough to give you an idea of what you can do with the system. There's a lot of information on the website. This is the new website. As I said, it went up, I think, yesterday or the day before I finally brought it up. Now I'm a web designer. And it still, though, is part of GitHub, and nothing's changed. If you've been there before, if you go to the GitHub repo button, you'll wind up on the GitHub site, which is where the actual bits are. And what we would start is you would go to the download zip, which would just take a copy of all the bits and bring them down to your machine. And just to save time, I have a folder sitting here which just brought the liquid master branch down. That's if I hit download zip, this is now sitting in my download folder. And I'm just going to extract it into C:\liquid. Actually, C:\/ will extract it into liquid. So we'll bring out the bits, and the only reason this is going at root, and I do this also on OS X and on Linux, is a really dumb reason. The actual simulator doesn't care. You can put it anywhere in the system you want. But tech cares. LaTeX has to find in an absolute path where the included formatting instructions are for the circuit diagrams. So if you want to change the first line of the generated tech files out of liquid, you can point it anywhere you want. But by default, it's looking in root liquid is where it's looking for that file. And that's why it's sitting there. So we extracted it. Let's take a look at what we got. There should be a liquid master directory. And since it got renamed by GitHub, we just really want to call it liquid. And that was the entire install. We're done. If you take a look, what comes in the kit, there's a binary directory. The binary directory has the executable, the libraries, everything you need to just run. You don't need anything else, and you can just run the system. The docs directory has a 100-page PDF user's manual, 700 pages of API docs. It's also got this tutorial script in it, so if you also want to just go through the steps that I do, it's already there. Image directory is just used by GitHub to put up the images that we're using. Linux is the same as a combination of the bin and the source directory for the non-Windows machines. It's actually the same bits, same binaries, but the solution file, the actual IDE project for Xamarin and Mono are different than it is for Visual Studio. So that's why there's a Linux directory. Samples, we're going to spend a bit of time in near the end. That has all the quantum chemistry in it, all sorts of scripts, how to run the system in various different modes other than writing code and compiling. Source is we're going to write source code, and that has the project in it that we're going to use. And there's a new area, user code, that I just added recently. This is for anyone in the community who wants to contribute code back. And currently, I'm the only one who's contributed code back that we're going to make available for people. The one that's in here is how to read the circuit data structures and generate your own output for your own simulator. For instance, the example I did is for CHASM. So those of you who want to talk to Scaffold or anything else that might use CHASM, this was an example of how to go into Liquid, generate a circuit, and then dump it in another format for somebody else's simulator or compiler. Okay. So now that we have it, we want to make sure it works. So I'm going to go and start a terminal window. I'm going to go into the root directory and go into Liquid, bin, and we'll run it. Now, if you're on OS X or Linux, it's mono space liquid.exe, and it's a capital L because the operating system is case sensitive. So be forewarned to get it to run. But I'll say liquid, and the first time you run it, it's going to complain that you haven't accepted the license. Only time you'll ever see this, you type a yes, you're now legal. What's more important, that actually goes over the net and sends back to me that you're now a registered user, so we know how many users we have. This is how I get funding, so it's a good thing. But that's all. It's all anonymous. We don't know who you are, anything else about it. We used to have you registering for all sorts of things. We got rid of it, but on the website, you can register for the listserv. I would encourage it. That's how you'll get told there's new releases, or we have new bits available, or things like the Quantum Challenge that we're hosting. All of that will come over the listserv. It's very low volume. Maybe once a month, we send out a few paragraphs. That's about it. Anyway, we've now accepted the license, so we'll do it again. And now we get all sorts of output. So let's go back and see what it did. And what it did is it noticed that we never gave it any arguments, which is not legal. And it says, oh, you must want to know what to do. And so here are all the built-in examples in the executable that you can run. And we're going to run through a few of them and play with them, but they're all documented in the user's manual. So everything you see here, anything I don't mention, don't worry. There's full documentation on all of it. So if we go down to the bottom, there's some command line switches. We'll use a few of them later. For right now, let's make our life easy. Let's do something we care about. Let's factor shore of good old 15. So you get a bunch of output. It's going to tell you what it's factoring, how many qubits, what the coprimes are. And the m's coming out on the right, m equals, is the quantum result each time we're running a phase estimation. And sure enough, we got an answer out, and it was usable, and we got that 15 is 5 times 3, and we succeeded. Not very impressive, but it works. So sure works. We could do a little bit better than that. Let's factor 55. So 55 is a 15 qubits to do it. We're doing a 6-bit number. We're also telling you what the probability is of a random guess, being able to use that as the classical result to get the answer, and for sure what the expected worst case probability is. And now you notice the bits are coming out really slowly. I mean, this is a lot bigger. We've got a lot more gates we're doing here. But it's solving it. It'll take a while. What I'm going to do is change the last parameter from false to true. What this does is says instead of running the raw naive circuit that came in, optimize it. Now look at the speed of the bits coming out. We just went from 30,540 gates and reduced it down to 1,200 gates. So the amount of linear algebra we have to do is way reduced. This was that optimization slide I had this morning. There's a lot of things there that we're able to do, and this is how we're able to get up to a 14-bit number, or 31 qubits we're able to factor because of all these optimizations. And it worked. 55 is 11 times 5. By the way, if you put an illegal number in, it'll tell you what are legal numbers to factor with sure. So you don't have to try to remember which numbers work and which numbers don't. Just put anything in, like any even number, and it'll come back and say, no, 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 here are the numbers you want to use and why. So sure works. And we didn't, if people have been asking me, where's the source for sure? We didn't make it available for actually a reason that has nothing to do with, you know, I want to keep something quiet. It has to do with this is an academic release, and a lot of the instructors want to do classes want their students writing their own code. So we're not telling you necessarily how to write Shore, but we're telling you what papers we wrote it from. And if you want to implement it, you know it works, and you can compare it against this. So we didn't give you the source to Shore, but someone on the website, for instance, couldn't figure out how to do a quantum Fourier transform, so we wrote one and put it up. So we have nothing, there's no hiding here of the actual code. It's more the case of we want students solving things themselves, what they need to do. So Shore is there, it's fully implemented and works. Let's take something a little simpler. Let's take the quantum hello world of teleport and run teleport. Now, we ran 3 sets of teleport runs. I want to talk a little bit about each one of them. So the first set, we ran, I think there's 10, 1, 2, 3, 4, 5, 6, yeah, 10 of each one. We're just taking a random state vector, setting it, run teleport through, introspect, look in at the state vector, we can do it because it's a simulator, and see that the full floating point value all matches. We actually did teleport. And at the end, you'll see there's bits, colon, 0, 1, or 1, 0, 0, 0. Those are the X, Control Z gates at the end to get the value out of teleport. So this is actually saying do a Hadamard, do a C0, just calling the functions, running through, running teleport. Then we take that set of functions and we introspect it back and make a circuit out of it. We're going to generate drawings for the circuit. We'll show that in a second. And then we're going to run the circuit. So the second set is instead of calling the functions, we're actually taking the circuit, interpreting the circuit, and walking through the circuit, running it, and it works again. We get the same answers. Everything works. And then we run it through the optimizer that we just used for Shore. In this case, all we did was drop from 8 gates to 5 gates. It's a pretty simple circuit. And ran it, and again, we get everything works. All our vectors are getting teleported, and we're getting different results for each one. So these are the 3 different modes the simulator will run in. You can run it directly on your functions. You can introspect it back, take circuits, and run them directly, or you can manipulate the circuits, optimize them, make changes, do gate substitutions, all sorts of things, and then run it through again. There are 3 simulation engines in the system. There's a universal one, is the one we've been using. There's a Hamiltonian one, which is the same except he understands time. That'll let us do quantum chemistry, quantum materials. And there's a stabilizer simulator. Stabilizer simulator a la CHP, Scott Aronson, equivalent sort of thing. That one, there's no limit on the number of qubits, by the way. When I said this morning there was 23 qubits, the stabilizer you can do as big as you want. We've done tens of thousands of qubits. So when you want to do Clifford operations, you want to do quantum error correction, that will let you play with those circuits and actually run through, do surface codes, things like that. So once we have this, I said we generated some drawings. Let's look at the drawings. So if I look at teleport cf.htm was one of the files created. There's our teleport circuit. And this actually is a little more sophisticated than the one I was going to first show. Let me show you the one I was going to show first. And he is here. Sorry, this one. You'll notice, for instance, each gate is at a point in time. By default, when the circuits are generated, everything is sequential. The other one I said fold this. Well, there's not much to see, but the 2 measurements wound up on top of each other. Everything tries to fold to be as parallel as possible in time. And so you can rewrite your circuits. There are all sorts of different rewrites you can do, but these are, 2 quick examples. We can also say what happened after we optimized it. So we dumped the circuit after the optimization, and now the Hadamards and the C-naughts all got collapsed into a single matrix. The system will make a random 8-digit hex name for it and fill the system as it's optimizing, and so this way you get just bigger and bigger matrices that are more and more efficient for classical simulation. But you can draw any of this, so you can see them in the drawings, and you can also get tech out just as easily. So let's look at the Latex file. I have TechWorks installed here. You can use any LaTeX that you want. It's all compatible. We're using TIC-Z for the drawing package. And for some reason, TeXworks takes forever to come up. Forever is about 10 seconds, but forever to come up when you start it from a file. We don't know why. There we go. And I'll say, build the LaTeX, and there's your drawing. The nice part is this is actually laid out in the source TeX file as an array. So the circuit is just laid down in the array. You can go in by hand and edit. So if you want to put dotted lines, you want to comment, change things, whatever, it's designed to do publication quality graphics that you can sit there and then drop these as figures into your papers. So it just makes it really easy. This is the one feature that when I wrote it that I didn't think anybody really cared about, and my researchers have just gone nuts, the fact that they don't have to hand draw everything that they do. So this has probably gotten used almost more than the rest of the simulator. It's just the rendering package. Okay, so let's actually do some programming. So I'm going to change into the Liquid source directory. If I could type. There we go. And one of the files in here is a liquid.sln file, which is a solution file. That's the Visual Studio IDE controlling file. There's an equivalent file, again, on the Linux side for Xamarin and Mono. And we'll bring this guy up. Since it came from the internet, it's saying, are you really sure this is safe code? You know, the usual type of thing. We're very careful. But we're going to trust it. Team Foundation server, really? Okay. Let's go look at our project. So here's our code that we're going to edit. It comes with a package or a file main.fs, which is just a place to put your bits. And I want to point out a few things that are in here. We'll go through the whole file, but let's just do this in the order we're going to use them. There's a tag, this LQD tag. Anywhere in the system that you put that in front of a function, that's now callable from the command line. So this is how you add things to the system. If you want to add your own command, you say liquid of this function, you know, my function foo, you put this in front of foo, now foo's available from the command line. And you can hand it all the arguments, anything it needs, it gets parsed, handled, it gets added into the system. So this says this function user sample is callable from the command line. You'll notice all of my built-in examples start with 2 underscores. That's just convention, just so you know I wrote them. You can name your functions anything you want. And then there's a line that says show and a string. Show is printf, okay? But why am I not using printf? Well, it's actually much more useful. This one puts a new line at the end of the line. It's thread safe. If 100 different threads are writing at once, they all come out without tearing on top of each other. It knows about the log file. I can put things on the console and the log, or just the console. And show controls all of that. I can open and close log files underneath, and it'll send them to different files, all sorts of utility. So just in general, use show, but the syntax is printf, and everything in printf works in it. This is what you'll see me use throughout the system. So the other thing I'm going to do is I'm going to open up the project itself, liquid, ask for its properties. And in the properties, I'm going to say I want to call, instead of sure, when I run it, I want to call user sample. And while we're at it, why don't we work everything in release mode so things run as fast as possible? So what I'm going to do is I'm going to say I want to start this without debugging, which is Control F5. Because we're going to do this over and over. And this way, we don't have to keep getting out. We just say, run this. It compiled it, linked it together, starts it up. And every once in a while, maybe it's an Apple hardware thing. Is that a good way to put it? Yeah. Things go slow. And we ran sure, because I forgot to change it for release. I changed it for debug. So change this to user sample. And now we get this is the string that was there, and it prints it out. It says it opened the log, wrote the log, closed the log, and everything exited. So we run. That's a really simple example, but we know we can compile, link, and run, so this lets you know your system's working. So now let's go back and actually write some code. I'm going to write a routine called QFunction. So it's a quantum function, and it's going to take one argument, which is a list of qubits, built-in data type. Everything that's quantum in the system, the last argument of the function is always a list of qubits. Convention. But everything counts on it. So for example, if I say Hadamard, list of qubits, it'll take a Hadamard of the first qubit. If I say C0 of a list of qubits, it'll take a C0 of the first 2 qubits. So if a gate knows how many qubits it needs, it reads that many off the list and uses it. So why bother? Well, what if it's a quantum Fourier transform? If I say QFT of a list of 10 qubits, you get a QFT of 10 qubits built, or 20, or however many you need. So this lets you just define your functions uniformly throughout the system. If they know how many qubits they take, they just use that many. If they don't know, they use the list as telling it how many to use. Any extra arguments you have, we'll do that in a couple of minutes, come before the qubits. The last argument is always the qubits function. So you'll see that throughout. And all I'm going to do here is I'm going to make a function that does something completely trivial. Measure the list of qubits. In this case, measurement. It's a measurement in Z, takes 1 qubit. He's going to take the first qubit off the list and measure him. Okay, that's our function. For user sample, we're going to set aside an array for statistics. We want to see what we're running. We're going to gather some statistics. So 2 integers of value 0, we're going to just put in the array. What we're going to do is every time we measure 0 or 1, we're going to increment one of the elements in the array, see what we get. We also are going to need a state vector. So we'll create a ket of 1 qubit. So we now have a state vector. We created the qubit. K is the ket vector. You also know I'm surreptitiously teaching you F# here. If you know Python, if you know Java, if you know any block structure programming language, it's about 10 minutes to learn what you need to know to use F#. And if people want to really know why it's an F#, buy me a beer and I'll tell you all the details of why I like the language. Okay, so for loop, for I in 0 through 9999, 2 dots. So we'll do 10,000 iterations, do. Well, every time we go through, we're going to do a measurement. We're going to destroy our ket vector. So I'm going to reset it back at the top of every loop to one qubit in the ket vector. We're going to reset it. Now I'm going to call our function. So we'll do whatever the function says to do. And now I want to see what we got. So I'm going to let a value is pull the head of the list of qubits, get its bit value. Bit is a built-in liquid type that actually takes on 3 values. It could be 0, it could be 1, or it could be unknown if you haven't measured yet. So it's not an integer. It's something that understands a quantum type, whether it's been measured, not measured, and what the value is. In our case, we know it's been measured, so I'm saying really pull out the integer value. So V is now the integer value of that first qubit, and we're just going to say the stats, get the stats for that value plus 1. So we've gathered our statistics. And at the end, we're going to do a show that we measured 0 equals a %d, 1 equals, as I said, printf syntax, stats.0, stats.1. That's it. That's our whole program. Nice and simple. Except I'm not, just like Python, you need to be indented correctly. Good. So we'll run it. This isn't going to be too exciting because all we did was create a state vector, didn't do anything to it, and measured it. And when we run, we'll gather it, do it 10,000 times, output statistics, and sure enough, we measured 0 10,000 times. So we have classical code that works and compiles by using qubits to do the classical code. Okay. Now let's do a little bit better. This time, we're going to change our Q function, and before we do the measurement, we'll do a Hadamard. So this time we'll throw everything into a 50% superposition, and then we'll do our measurements, and lo and behold, we got 5,026 zeros and 4974 ones, which is about what you'd expect statistically running through the random number generator and getting about half of them are 0 and half of them are 1. And every time we run, they'd be different. By the way, I did this at Delft 3 days ago, and I got exactly 5,000. I've never seen that. And I don't know what the odds are that that could happen, but I actually had to run it again to prove to them I didn't just have this canned and set up. Okay. So, not too bad. We've actually done something quantum for once. We actually did superposition. I now want to show you what it takes to do your own gates. It turns out there's nothing magical about Hadamard or CNOT or anything. They're really just data types that are pre-created for you, but you can throw them away and make your own. You can add to them, you can change them. If you want to make them fuzzy, if you want to do correlations, if there are all sorts of things you could do, make your own gates. So I don't have to type it here. I should actually have made all of this bigger probably. I don't know how readable these are, but let's make that at least 130. This gate rot_x is something I typed in earlier, which is just a rotation in x by some angle theta. And sure enough, there's a gate data type. You can extend this type, you can give it a name, help, there's all sorts of fields. But more importantly, for a simple gate, there's a matrix. So you just create your unitary matrix, you drop it in, and it's now a gate that Liquid knows how to use. So we took the cosine and the sine from the angle, we generated a complex sparse matrix, it's 2 by 2, put the values in, and then there's a drawing line that actually calls the tick-z macros that says, oh, I want to make a box, I want to put this title in the box, call it a gate, here's how many wires it is, dot, dot, dot. All this happens for you. Again, all of this is documented in the user's manual, how to write your own, also how to do metagates, higher level gates, how to do gates that are computed on the fly, all sorts of things that you can do with it. And at the end, the gate runs itself when it's asked at that angle and uses the qubits. So instead of the Hadamard, I'm going to change that to our new gate, rot_x. And I'm going to give it an angle of pi over 2. So we'll compile it again, we'll run it, and we got the same type of answer. Because instead of going around z, we went around x, but we did also still pi over 2 for our angle, and we got the same thing. So you can write your own gates, you get the results you expect, but then again, I want to prove that we really did this, so change the pi over 2 to pi over 4. Okay, why did we get 8537? Turns out the cosine of pi over 8 squared is 0.85355. And so that's actually the probability you'd expect from a pi over 4 rotation. So that's all there is to building your own gates. And you can make these multi-qubit, you can build anything you like. If you have gates that are not built into the system or specifically say for optics, things that you're doing, just change the gate. Put your own unitaries in. We don't care, it all works. So we've done classical, we've done superposition, thing we're missing is entanglement. So I'm going to change our function slightly. And what I'm going to do is I'm going to say, let's use the rest of the qubits that come in the list. We already took this rotation on the first qubit, but now I'm going to say for q in the qubits in the tail, everybody but the first guy, I'm going to do a C0 of the head guy and this qubit. So what am I doing? I'm going to do a rotation of the first qubit and then C0, 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 all the way down to anybody else you hand in. So we're going to entangle everybody together. When we're finished entangling, instead of just measuring the first qubit, we'll measure all the qubits. The little bow tie operator says, take this quantum gate and map it to everybody on the right. So this just mapped a measurement across all the qubits. So we're going to build up a giant entanglement and then rip it all the way down by measuring. Of course, if everything works right, they should all measure the same. They're all entangled. So we'll make sure that that's true. We have to change the code now to actually do a list of qubits. So I'm going to change the user sample to be, take an integer. So the guy we're calling from the command line now takes an integer of how many qubits you want to do. The ket, instead of 1, is now n qubits. We're going to reset it to n qubits. Everything else looks the same, but after we take the statistic on the first qubit, I want to look at all the other qubits. For q in q's dot tail, do, and if the head qubit bit value doesn't equal this qubit bit value, we have a problem. So we're going to throw an exception. We're going to say fail with different, and the world will blow up. So it better be the case that not only we get a random value, or actually we get a specific probability value out for the statistics, but every other qubit had better agree with it as we do the measurements. So we'll run it. And we blow up. And if we go through the details of what's happening, it's saying you called user sample without an argument because we didn't have one before. Nice thing about F# is everything is fully type safe, fully checked statically at compile time, and the system understands if you change the type of an argument or the number of arguments or anything, it will not let you run through. It will make sure you do things right and keep you honest. So we now are told that we want 10 qubits, and we're running, but nothing's happening. Well, nothing's happening because we're entangling 10 qubits together, building this giant state vector, and then we're going to measure it and bring it all the way back down, and it's going to take a while. And so eventually, there we go, we got an answer. I should have mentioned what the numbers at the beginning are. The other thing show does is tells you information about the output. The number at the very beginning in front of the colon is the thread number that the output came on. So if you do multi-threaded output, you knew which thread is talking to you and where they're coming from. The other numbers are minutes. So this was 0.3 minutes to run, or 18 seconds approximately. And so you always get an idea of how long things are taking to run, what they're doing, and this happens for free when you use show. You get it in the log as well as on the console. So this took about 18 seconds. We got the same statistics, that's good, and it didn't blow up saying that they didn't agree with each other. So everything is good, but we'd like this to run a lot faster. So now we want to write optimization for this. So we're going to take this guy, and all I'm going to do is, at the very top before the loop, I'm going to create a circuit. There's a static method on circuit called compile. I can hand it my quantum function, and I, of course, have to hand it qubits to use, because, again, if it was something like a Fourier transform, it wouldn't know how many qubits it should compile for. So you have to give it a list of qubits that you would have called the function with. It's not actually running the function, but it needs to know how to interpret the function. So what this will do is create a circuit from all of those calls and hand it back to you. It didn't actually run it yet. Instead of running Q function now, we're going to run the circuit. So we'll say circuit run. So all we've done is taken all our function calls, converted them to a data structure called a circuit, and then told the circuit to run. We're not any faster. Well, why would we be? We're doing the same number of operations in the same way. If anything, we're slower, because we have to interpret a circuit now instead of just running the functions. But it's actually not noticeable. It'll be about 18 seconds again, and it'll finish, and there it is, and we got our answer. But this time we ran the circuit. However, now that we have a circuit, we can do some magic with it. So we're going to take that same circuit, and I'm going to tell it to grow the gates together. This is the optimization call. There's all sorts of arguments that you can set. Oh, I have to tell it the ket vector to use. There are all sorts of options. You can say how you want it to grow and densities and all sorts of things you can do. To be honest, the default built into the system is pretty good. In fact, I hardly ever hand it the arguments, but they're there. So let's run it. And instead of 18 seconds this time, it took something under 6. So it's a factor of 3 speed up already. It's a really simple, small circuit, but it works. And so you can optimize your circuits that easily. All you have to do is do a call through grow gates, and you're up and running. So all of that got us to circuits, got us to optimized circuits. The next thing, since we have a circuit, let's draw it. Let's see what they look like. So after we made the first circuit, I'm going to say show test 1 just as a label so we see what it is. And then I'm going to say dump, obviously, and render. So first thing we're going to do is take the circuit and say render. Render. Render is the drawing package. I want HTML and LaTeX, or tech, and I'll give it a name. That's the name of the file. Again, all sorts of arguments. You can split figures, you can scale them, you can do all sorts of things. Let's just take the default. And also, in the log, let's put a dump of the circuit. Let's look at the actual circuit elements. I'm also going to take this same code and do it after we optimize it. So we'll call that test 2. And we'll run. So now we built drawings. Those are the first 2, and it's going to run. It'll take another 6 seconds. I think I'll just kill it and move on. But we have the drawings. So let's look at the drawings we just created. So if we go to, we're in the bin release directory. You'll see that we have a test1.tech in HTML and a test2.tech HTML. If I look at test 1, there's our drawing. So there's our ROT-X gate that puts its name of the rotation, says RX, and the rotation value, and puts it in the gate. There's all the C-naughts we did, and then there's all the measurements. So that's exactly the circuit we would have expected. And if we look at the optimized one, what we see is all the C-naughts were compressed all the way down into one array. And they went away, and it turns out it wasn't worth it to add the rotations. The densities became such that it would have made it actually slower, so it left the rotations outside. So it did the one rotation, it's non-entangled, it's cheap, and then it did all the C-naughts as one operation. There's our factor of 3 speed up. Of course, each time we've been doing this, we also do get a log file. So let's look at the log file. If you're playing along, N is my editor. That's not built into Windows. Liquid.log, and let's make this a little bigger. Oops. All right. And so if we take a look at the log, what we see is here's the dump of test 1, and there's a sequence of gates. We're applying a gate. The gate is our Rx gate with this name. Here's the help value. Here's the matrix that we defined. And then these are the wires it was called with, because it was called on all 10 wires. It's only using the first one. Then we're applying a C-naught, and there's the matrix for C-naught, no surprise. And then somewhere near the bottom here is all the measurements. So here's each measurement where the unitary is just an identity, because it's not a unitary operation. So the matrix is just left there as an identity to tell you that, oh, we're really doing a measurement gate, and we're collapsing this. There is no joint measurement. We're not in a weird basis. Again, we can do all sorts of things in the system. The second version is a little more interesting. The rotation looks the same, but now that set of C-naughts is replaced by this gate that's this giant sparse gate that just shows you where all the ones are in it. This is the C-naught that was built, or the multi-C-naught for over 10 qubits that was built. And it goes on for quite a while. And then finally, at the end, you'll see there's our measurements again. So the log, you can put all sorts of extra information in. You can put things only in the console or only in the log. All of that, again, is documented of how to do it. But that's really it. We just programmed a circuit from scratch, optimized it, got drawings of it out. We're able to run it, play with it. You can get gate counts. You can do all sorts of other manipulations. So what I'm going to do now is switch modes. And I'm going to go into the samples directory. So let's do a little quantum chemistry. I'm going to run from the binary directory the liquid that came with the system. And I'm going to say do chemistry on hydrogen 2, H2. So we run diatomic hydrogen. And that was it. It probably went by a little too fast. But what happens when you say _chem of something, it goes and finds a file in the samples directory that has the information of what that molecule is. So some are built in, and you can also add your own to the system, all that you want. Sorry. If we look at the log file now, what you'll see is there's all sorts of parameters we can set. We'll set a few of those later. But when you get down here, here's the Hamiltonian terms that were read in, that were built, what we built. And then we took a look and said, okay, the analysis, there's 87 gates. These are the different types of gates that are in the molecule. Then this guy does a different optimization. Besides growing gates together, it understands the physics of the problem for chemistry and materials. It understands that the number of electrons coming into the matrix has to be the same number as coming out. The angular momentum is conserved. The fact that if there's an even number of electrons, we're looking for ground state, half will be up, half will be down. Take all of those different types of things. Those are rows and columns you can zero out in the matrix. You just start decimating the matrix because they're non-physical states. It's impossible for those things to happen. So when we do, the next thing we'll do is water. Water is natively a 32,000 by 32,000 array if you wanted to build the whole thing into one array. Once you do this, it's 441 by 441. It's tiny. So then what we do, we build this whole thing down into a single matrix instead of trying to optimize for what's the best way to combine them. And now we exponentiate the matrices. By the way, when you exponentiate, especially complex numbers like this in big arrays, you're going to drift. Your numerical precision is going to go off, which is why you see this fixed unitary line. We actually watch how unitary the array is and fix it as we're exponentiating to make sure we stay unitary as we go. So in the end, we did a 28-bit phase estimation, a trotter of 32, and then this is a run of all those matrices going through all 28 bits and getting us, in this case, an answer of -1.137266 for the ground state energy. That happens to be with nuclear repulsion, and the 1.85 is without nuclear repulsion. Here are the actual phase estimation bits that came out. And at the end, we also give you, we also give you a probability. I just erased it, isn't that interesting? Go down to the end. I give you an overlap for the matrix itself. So if you look, tell you what, let's go to the next one since I seem to have fat-fingered it. There you go. This 98.7 is the overlap of the final solution as compared to the Hartree-Fock initialization state we started in. These are tiny molecules, yeah.
Did you diagonalize the matrix?
Nope. Nope. We took the whole thing up because I made it small enough I can handle it. So I actually decimated, so I took this giant sparse matrix, made it dense, tiny dense, exponentiated, and re-expanded back to sparse. And that's how we did this. So, but H2 is, really simple. I'd like to show you the input for it, so let's just do that. We'll open H2, STOG. This is a Slater-type orbital, 3 Gaussians, sums of 3 Gaussians, and this is it. There's not much to it. The 0, 0, 1, 1, and down are the actual integrals that came out of the classical quantum chemistry package. It says if you have 2 nuclei of hydrogen and they're this far apart, this describes the orbitals. And so this is the orbital integral information. In the system, in the samples directory, is an example of how to run these quantum chemistry packages. There's 2 examples, one for running PiQuante, the other for running Psi4. And so you want to design your own molecules, we show you what you need to do your own molecules, get these integrals out, and run them in the system. If you'd like to see something a little more sophisticated, let's look at water. So here, and there's a bunch of molecules come with the system. Here's water, and as you can see, there's a lot more terms. And so these orbitals then get compiled by the system, converted into spin orbitals, and are then built into a full configuration interaction model, which is why we get much higher accuracy than, say, this Hartree-Fock number that comes out of the classical chemistry package. So let's do that. Let's do a couple of quick things here. We'll take this run that we just did, and just to show you that Windows does have everything built in, that's the equivalent of grep. This is the sort equivalent. And so we'll run the system with what's in Windows, and what I did is sorted by the energies and just pulled out this CSV line, which is there for statistical purposes, because you can just pull out, we did 10 plus runs, and you can see the energies aren't identical. We didn't get all the same energy out, but if you look down at the bits, it's really because the last 2 bits are changing. And the last 2 bits are changing because in this example, I pulled a phase estimation technique that uses an arctangent at the bottom. This is Hastings and Savoy phase estimation algorithm, that those 2 are somewhat random, but it gives you an extra bit of accuracy as you're computing. So you get 3 bits instead of 2 out of the same accuracy calculations. But it does mean the bottom bits are going to move around a little bit, the bottom 2 bits. So this just shows you that it ran and it worked okay. What I'm going to do now is run water. Makes sense. So let's take H2O. He's going to take a little longer. He's actually 15,000 gates. And what we're doing now is building that single matrix. So there's 344 matrices we're pulling together, or terms that we're actually pulling together. And now we're exponentiating them. We're going through, fixing the unitary. We get our, in this case, 28 bits, and now we're running water. So each one of these is a run of water. If we take a look at them, you'll see we're getting this energy of minus 75.7287, which is actually lower than the Hartree-Fock energy because it's a better estimator. We're running a trotter of 32 for this. We can change all of that. So what I'm going to do is, actually we should look at a little of the optimization. So let's look at the log file. And go to the top. So these are all various terms in water. We can prep what orbitals we want to use, where the electrons start in. We can set all sorts of ordering information, build these terms. In this case, there were 350 terms in the Hamiltonian, but when we finally built the orbitals, these are a list of some of them. It won't dump them all unless you ask it to. Here's our 15,000 gates, and then our results. And even for this guy, you'll notice that the results have an overlap of, where is it, 97.3%. So again, these are simple problems. It's very easy for the quantum computer to fall into the ground state because we're starting from a very high overlap. When that becomes lower, this becomes more of a research issue. But we also give you output like the occupations. So if you look at the occupations, the asterisk is every place we placed an electron at the beginning, and then the number is the probability of it being there or the magnitude of it being there at the end. So you can see that we actually guessed really well because these are all up at 1 and 996, 991. The probability of the electron winding up where we put it is very high in the end. All of this, again, is documented in the user's manual, and I encourage you to go take a look at that if you're going to do chemistry before you go off and play with the chemistry. So what I'm going to do now is take a different approach to this whole thing. I'm going to open up h2.fsx. An FSX file is an F# script file. So I'm going to do everything we've been doing, writing code and all, but doing it from scripting level like you would with Python from a script. This is a nice little example. The script itself sets a dictionary up of all sorts of arguments of what I'm going to do in the quantum chemistry. Instead of reading the hydrogen file with data, this is that same integral file, but I just have it directly in place here. So what this is I'm taking two atoms of hydrogen that start out at 0.5 angstroms apart, and I'm making further and further apart. I'm going to do a disassociation test. So each one of these tests has a molecule where I'm just spreading these guys apart, and I want to look at the various energies that are going to come out. So we've got 71 position or 72 positions, and then at the end, I define a couple of functions. Again, put that liquid tag, says I want to call this from the command line. So I'm going to call test and trot from the command line. Test lets me pick one of these tests. Trot picks one of the tests, but lets me change the trotter number, so I can change the accuracy of the interpretation. So if we now go back, bring back liquid again, and in fact, I'm going to do the same thing we did, but now I'm going to say I want to load this script, h2.fsx. That's going to read the script file in, compile it, generate a DLL, output the DLL, and then load the DLL back into itself. So we're adding this code to the system, and now, instead of calling chem, we're calling that function test on, let's say, test 26, I think is the one that's closest to what we've been running. So we're doing this compilation, the load, the reload, and we ran. And we got an energy of about minus 1.13727. What I'm going to do now is instead call the trotter call with a trotter of 2, a really terrible approximation for the molecule. And what we'll get out is a much higher energy, minus 1.346. It's not very good. We can also go the other way and say, nah, give me 1,024 trotter steps. This problem is now 1,000 times harder, but we get energies down to 1.13728. And we're actually approaching what we believe the true ground state actually is for the molecule. So you can very quickly write scripts and then sit here and dynamically play with them, interact with them, change them. You don't have to go through the IDE and the compiler to do things that you know you're going to do a lot of. Another word about documentation. So let's go into the docs directory. There's a PDF file, 100-page user's manual. It's got every subject covered in it. All the samples are in it. And all sorts of examples of how to write code, how to work with the code, how to do error correction, noise modeling, different types of levels of output you can get, higher level views, lower level views on the graphics. Again, less detail, more detail, and alike. So I think almost everything you're going to want, you'll find there. If you can't figure it out and it's not there, definitely get on the GitHub site, put in an issue. We are very responsive if people are using the system and want to work. Here's an example of the quantum chemistry. This is H2. These are a high-level view of the terms versus the actual gate-level view of the terms. And so, again, you can dump all of this out. Also, in the same directory is a compiled HTML file, which is the full documentation for the API interface. So 700 pages in here. Let's go, say, into the circuit class. And why am I not seeing it? Okay. Maybe you know what it was? I didn't hit the check mark that says always ask. It's trying to ask on every file whether it's legal. That's a little better. So, circuit. Here's the circuit class we've been using. So there's our compile method, dump, the render we were doing, all of that. And everything has full documentation, typed arguments, what you can do with them. and it's all available directly. The website itself also has all of this interactively online. So if we go back to the website, the Getting Started has Windows, Linux, and OS X instructions that are just laid out nicely. It's just about 4 steps and you're up and running for everything you need, including the IDE. About will send you to the Microsoft Quark website with information about Liquid. I may not have an internet connection anymore. So there we go, I do. Cool. So this will tell you all about it and then let you get to the rest of Quark. There's also the full user's manual is here. The API docs are here interactively as HTML. And there's a support page that includes a bunch of little videos, like 4-minute videos on different subjects, and then this entire tutorial is there as a video as well. And I'm probably ahead of schedule, but it's probably a good place to stop and ask if there's questions or things you'd like to talk about. So, thanks. Okay, the system does not generate graph state representations, no. It only knows how to draw circuits, but it's a data structure. And for instance, in the example where I generate the CASM code, it shows you how to walk the data structures. So now you have everything you need of who's connected, where they are, output all the graphs you want. Yeah.
How is the fixed unitary drawing? Is defined by norm of the matrix, or is something more complicated than that?
I'm basically moving it back onto the sphere. So it's looking at how much it's moved off of the sphere and renormalizing it back to being unitary. This was a technique from Matt Hastings that he gave me. So the details, I drop Matt a line and he'll tell you what he's doing. Sure. It is still cheating, obviously, because you lose numerical precision, so it may not be the right unitary, but it's awfully close. Mm-hmm.
I'm wondering if you have any thoughts on how we can add leakage as a noise modeling.
You're going to be very happy. So among the noise models already there, the simplest one is the one for the stabilizer simulator, where you give it depolarizing noise statistics. You say, I have X, Y, Z at these error rates, and it just drops those gates into the circuit randomly. So this way you run, say, out on a cluster, thousands of runs, you run your noise through and you get what you'd expect for statistics. Second level in the universal simulator is a noise model that will let you put your own functions in. Now there's a built-in one for depolarizing noise, but it doesn't change the circuit. It's actually, as the gates are running, it gets called back. So we can call you back and you put in, you want to do correlated noise, you could do correlated noise. Among the things in there also built in is amplitude damping. So if you want to do T1 simulations and things like that, that's already there. And you can actually sit there and watch this thing hard fall off the edge as the qubit disappears and everything else moves and all of that. It's in the manual. There's a full description of both the formulas that are used and examples of a noise model, and that's in the samples too, is how watching these noises and tracking them. I will tell you, when I can get back home and finally get some sleep, the next thing going in is Kraus operators. So you'll be able to specify your noise in terms of Kraus operators, and you'll be able to get much more sophisticated noise modeling out of the system. It's actually no more expensive for the system, I just haven't written the code yet. I don't do density matrices, and the only reason I don't do them is you lose half your qubits. And I think we were small enough as it is, we can only get so much. The efficacy of the noise models only go to so long. So I've been fighting with some people who really want density matrix simulation. Not going to get it. But the Kraus operators get us to most of what experimenters want to show for their noise and what it's going to look like. And again, you can already do correlated noise and that. We've done a lot of noise modeling with the system, and it seems to work pretty well in terms of finding fidelities and thresholds and the like. So I think you can do what you want. Now, once you have that noise model, you could plug in at that callback time anything you wanted. So if you wanted to fake it out, you could, because it'll tell you on this qubit, here's the last time a gate was called. This is the interval of time since, here's the gate being called. What do you want to do at this instant? And so if you wanted to throw things in there on the side we didn't know about, you can.
Well, what I'd want to be able to do is to say, okay, with some probability, a gate actually would
But you can go in there and edit the state. You could change whatever you wanted to behind our back, right, in that respect. So if you don't want to just do both the unitary and then the amplitude damping as the non-unitary noise model, we don't prevent you from doing it. It's a classical simulator, so you can go into that state vector and do whatever you wanted to it. I'd keep it normalized, but other than that, yeah.
I think what that is getting at is, what if your qubits aren't qubits? What if they're actually Q-trace and you didn't know?
I do have on the list, can we get Q-trits? Can we get Q-dits? I've got a list that's about 8 pages long of what people want. What's in the simulator is what our researchers, basically Krista's team, has asked for their research. And so what happens is, as they decide, hey, I need this. Alex Bakharov would give me anything for Q-trits. You know, he wants them badly because he's doing metaplectic anyons and he needs Q-trits for that, you know, for example. It's more the case of the amount of work we have to put in and what the benefit is for the next things we have to build. And so we have this whole list of things. Like I said, the noise operators, the Kraus operators were next as the most useful thing, but it's on the list. The qubits built into the system are qubits. Okay, they don't know anything more than that. But you can always fake out the state vector where it doesn't know anything. It's a vector, it's still doing the math, it just doesn't know this is really representing Q-trits. So there's ways you could get around it, but it would be a little ugly, and the optimizations probably you wouldn't be able to utilize that type of thing. Whoop, I saw a hand go up and down. Yes? Yeah. Can you design qubits? Well, the only thing about a qubit that it knows is that it's representable by a 2x2, well, it's representable by a state, right? And it understands it has a 0 and a 1 state, and it's on a block sphere. So other than that, I don't know anything about the qubit. I don't know how it reacts, I don't know what it does. That's the gates that you define, or the noise that you define, and how you're going to perturb them. It's just that I'm assuming we have 2 levels, right? That's the only assumption in the design. Qubit is a very simple thing. It's just a name that says, in the state vector, this is the thing that's the qubit, and whether I've measured it or not. The state vector is actually much more complicated. Because, for example, if you had 20 qubits, I don't want to eat up 1,000,000 entries if you haven't done anything yet. So instead, there are 20 state vectors when you start out with 20 qubits, because they're unentangled, and each one is very tiny. And as you do operations, things start entangling, the state vectors start coalescing. And so under the ket, there's this data structure called a ket part, where the ket parts are all being pulled together and taken apart as you measure, as you entangle. And this whole system then lets you do the concepts of things like registers. I have 2 different registers. They're not entangled. I can be very efficient about the memory. By the way, the system will also let you tell it, I've just done enough operations that I know these registers are separable. So these are now something you can put back into parts again. That's very dangerous, obviously. But the system would have to spend a lot of time figuring this out all the time. So in general, it just lets you do it. But there's a flag that says, check me that I'm right. And it'll see if anything really was entangled when you say they weren't. And it'll throw up a flag and say, wait a minute, you screwed up. So once your circuit works and you know that they're disentangled, then you turn off the flag, and now you're running fully efficiently and less memory and all of that, because you said, at this point, these 2 registers really have become disentangled because we've gone back through the circuit and we've done the right uncomputing. So there's all sorts of things in that API doc of things you can do to make your life easy in terms of memory usage, in terms of optimizations, and so forth. Yep.
Yeah, so again, thinking about how I might implement leakage.
Yep.
And what you just said, I mean, can you dynamically add qubits?
Yes.
States in the system?
Yes.
So run into a memory limit?
Yes, well, memory, of course, is always the problem, but yeah, it's a 64-bit address space. It's all built, you can put lots of qubits, except in the academic release, 23 qubits, in the universal simulators is the limit. But dynamically on the fly, you can add to the state vector, yes. Now, and you can also, I said, split them apart. So once you've done that, they don't cost you anything. You can always bring them back, take them out. If there's things like if you had a bath and you want to couple to the bath. The way we do the amplitude damping is a 1-qubit virtual qubit that we couple to as a bath. And so we just bring that onto all the other qubits, couple them in, do the amplitude damping that way. It's exactly the example that's in Nielsen and Chong. Nothing more than that. Okay. Oh, no, we got more. Oh, behind you. Yep.
So I think I remember there's a paper called something like 18 long
Okay? Probably most of them, right? It's actually pretty straightforward because we make them dense first. When I was doing this in sparse matrices, it was really a problem, right? As dense matrices, we do pretty well, but you notice I'm going to a 20 to 30 bit phase estimation. That's a lot of exponentiations. You don't have to. If you're doing normal things in real life, you can do maybe 10, 12. We never go away from unitary. That's not really a problem. So I've got to be doing 20 exponentiations of a giant matrix before things look bad. So we're pretty stable. You know, we're being as close as we can in the exponentiation code to being as stable as we can. And we've done some numerical tests on it to make sure. Okay. I have to look in the code to see what I finally wound up with over these years, because it's changed over time. But it's probably, I'm trading off stability for speed, probably. I want more stability, and that's probably what I'm doing. But I don't think I'm being really that efficient in the inner loops or anything. I mean, I'm multi-threaded in all of this. So it's good, but it's probably not the best you can do. I should say that all the math in this is in F#. All the linear algebra, all the complex math. So it's not the fastest in the world, by any means. And this was a conscious choice. I'm probably no better than a factor of 2 or 3 away from an MKL or Godot Blaz or Open Blaz. But that's good enough, because I'm more worried about the exponential problems in terms of slowdown, and I want this to be easy to fix, easy to change, and I want it to do sparse linear algebra, complex sparse linear algebra really well. And it's hard to find packages that do that. So I bit the bullet, we optimized the hell out of it, but it is in a high-level language that's not C++. And so I know I'm leaving some crumbs on the table. There's somebody here who's been doing benchmarks I spoke to earlier compared to us, and they're faster, right? Yes, you know, you've got LAPACK underneath that, and it's, the hell has been optimized out of it. But for what I want, this is probably the best trade-off. It's maintainable, it's small, it's self-contained, you don't need any other packages. Like I said, that whole install was unpack it and run, and I like that. Yep.
Yeah, so I'm going to...
It's okay.
I have a question about the underlying math package.
Mm-hmm.
Suppose I, as a user, know of a way to exponentiate a random gate within my code. It's very efficient, more efficient than
Yeah.
exponentiation. Is there a way for me to hack in and say, okay, numerically, this is how you...
Well, you can do your own gates any way you want, and if you say, I'm going to generate the gate at this level, sure. To run the built-in phase estimation, that's going to be my exponentiation. The one that's there for quantum chemistry, quantum materials. That's a package you'd have no visibility into. No.
Right. I guess I wondered whether this interface can help me with the tensor product.
Oh, you can, it does. Kronecker products are built in, permutations are built in. All those optimizations I showed, those are there in the API set. Yeah.
I give it a manual 4x4 matrix.
Oh, you can.
It will put it to the right...
Oh, it'll do all the right things. Oh, yeah. That's all built in. You can also, there's mapping functions that say expand this out given these permutations, and it'll expand them out correctly for you. Because like I said, what we actually do, I don't know if it was obvious in the slide this morning, but we don't do the Kronecker product in the right order. We don't take the gate and tensor it with an identity matrix to expand it out to have it fit, because that spends the bits all over the place. We do it the other way around. We do the identity matrix with the gate. So now you get a block diagonal of the gate going all the way down. Well, that's wonderful, but the Kronecker product isn't commutative. That doesn't work. Well, it does work if you permute everything. So now you have to pre-permute, do that, post-permute. But if you keep doing it, don't post-permute. Just keep permuting every time as you need things. So we do all of this work to do as little movement of data as possible and keep those bits as tiny as possible. Keep that little matrix coming down the center so the linear algebra is efficient as we can get. Again, that's why I'm even close to a factor of 2 or 3 from a regular linear algebra package, because I'm doing all of these tricks to make it do as little work as it possibly can. Yeah. Correct.
So my question is, can you estimate how much of the speed that you're getting by optimizing this way?
Oh yeah, because I can run it without the optimizations. I can compare. So if I run water, water here now takes about 20 seconds, right, to build the circuit to the end and run it. Without the optimization, first version of the simulator, before I had all of that, we're talking an hour, hour and a half to run the same thing. So there's your factor of speed up between them. But it's apples to oranges. Again, a quantum computer couldn't do that, but the quantum computer could do giant systems that I'm never going to be able to do. So I'm doing what I can to simulate what you would do, but the fact that I can run faster just means I can keep up to maybe 30 qubits, and after that I fall apart and it's never going to work. So I haven't spent too much time. We do a lot of work, though, on real optimizations for quantum computers. That's different. So for instance, when you do those Hamiltonians for quantum chemistry, you can use different circuits that we've come up with that instead of having the general circuit looks like a basis change, a bunch of C-naughts, which is a Jordan-Wigner string, a rotation, you undo it, you undo it. You put these next to each other and run. Well, this can be rewritten to take the basis changes inside and put the C-naughts on the outside. Well, now, if you order things right, you have this string of C-naughts going like this and like this and like this and like this, and they all cancel. So if you do it right, you order your terms correctly and you're intelligent, you can get, that's an order of n right there, n to the first reduction in those giant reductions we did for quantum chemistry. That's one of them right there. Get rid of all the Jordan-Wigner strings by being smart with the circuit. You can also parallelize. Instead of doing the C-naughts coming down like this, you do them to an ancilla. So you're gathering parity. All they are is a parity check for fermionic computations. But now I can put n ancilla and nest all these circuits inside each other. And we've done that. We get an order of n speed up again by nesting everybody inside of each other, but you have to add in qubits. So now you're trading off qubits for circuit depth, the usual thing. So the system actually has all sorts of ways of doing these things to statistically show you what you get when you try various tricks for the quantum computer versus for the classical simulation of the quantum computer. So we have two different classes of optimizations that we do. Yeah.
What's the size of your development team?
Me. 30,000 lines of code. This is what I do. Now, I should say, there is someone doing solid. There are people working on Q codes. Liquid was my baby. Now I actually have a team doing all sorts of other things, too. We also do the cold logic. So I've got an engineering team, but when it comes to the simulator, that was mine. Yeah.
How smart is Liquid about throwing out pi over 2 decay rotations when k is really big?
It's not, but it would be an easy rule to add. It is smart about knowing that two unitaries next to each other cancel each other out, that type of thing. So it'll figure out two Hadamard should go away if they follow each other in the circuit, and things like that. The rotation stuff is pretty naive, but it would be easy, if somebody said, oh, I've got a set of rules I want to do. No, but you could easily. Now again, the data structure for the circuit is fully transparent and available, and you can sit there and write that code. So all you do is have the system create the circuit, rewrite your circuit, hand it back and say run it, and you'll have everything working the way you want. You can then check how much you're off by when you perturb the rotations, that type of thing. We also did a module where we replaced, of course, every rotation with HST gates and did all of that work. So a lot of that was in the papers on gate substitutions. The system will do that. I should say we've ripped all of that out of the version we shipped. So anything that was real research is ours. That's not part of the base simulator. So the Hubbard model isn't there, and a bunch of the DMFT stuff isn't there, and so forth, because that's individual researchers' research. It's not my simulator. Yeah.
Is there a natural way to declare a bit as classical? Meaning it's unknown, but it never goes into entanglement?
Well, it can't be unknown if it's classical. By definition, that's quantum in the system. Now, in answer to your question, you can define anything to be a class. You could define it as have been measured at the time you defined it. So now it's a classical qubit. It's a 0 or a 1. It's known, but it's a qubit still. You still can't do any quantum calculation with it, but it knows it can be used, for instance, as a classical control in a circuit like in teleport. And you know it's now classical. It'll show up in diagrams as classical. That you can do. You can also resurrect qubits. You can say, after measurement, I'm going to resurrect him back to being an unknown qubit. Or I can resurrect him in state 0 or 1 or the last measured state. All of those are options. So after measurement, you can reuse Ancilla, of course. You don't have to just create new qubits all the time.
I guess I just mean as an argument that the function.
No, qubits are qubits. It doesn't know any difference on the qubits. By the way, there is also joint measurement that's non-destructive. So we'll do the projections and let you do multi-qubit measurement, get a parity out. And this is how we, for instance, simulate the braiding for the Majoranas. We actually do the joint measurements that are in those circuits, and you can do those in arbitrary bases on each of the qubits. Problem is there's just a lot of stuff there. So it's just, you have to dig and see what's there, and if it's missing, we can always be convinced there's something that should be added. I didn't say you succeed, but you can always try to convince. So the last piece I'm going to mention was the quantum challenge. I mentioned it this morning, but we are trying to get university programs to use the simulator. We're trying to get it adopted, and as part of that, we're just giving awards for people who want to use the simulator for something, specifically for academic projects. The first version is going to end at the end of this month, the first run of it. We'll see how well it went. We've had over, I think we're up to 300 people have applied. At the request of the community, we got yelled at, people wanted teams, so we allowed up to 3 people on a team now. And we've had all sorts of interesting submissions. They're starting to come in over the next few weeks. It looks like people are actually going to be bringing them in. We will keep running that probably every 3 months. It'll just be rolling that we're going to be doing it. I've had some universities have decided they're interested and want to add it to their program. In fact, next week, or actually this week, at University of Washington, they're using it in the class for the first time. So even locally, we're starting to get some interest. And I encourage you to go to the website and kick the tires. It's easy to play with and see if it does what you want. Yeah?
Do you provide any additional teaching material to go with this?
No, I'm actually trying to do it the other way around. I'm trying to get somebody to do lecture notes that we'll put up, if they want to teach a class with it. Because it's really, even Ike Chong was interested, in doing this, and Krista's interested in doing a textbook based off of it, right? But it's getting the time and getting commitment. I think over the next year, you're going to start seeing stuff. It may even come up through edX, from Delft. They may do it through there as an online class and make it available. So there's some interest going on, but I haven't gotten firm commitment. It's really hard to get firm commitment before someone has to do a class and needs it, and then they're going to want it, and then it'll happen. Yeah. We actually had 2 submissions from high school level. The problem is our legal department gets all concerned, and they have to have a parent sign and things if they're underage and all that. But yeah, I want everyone using it. That's no problem. It's the quantum challenge. It's more what our legal guys say we have to do, don't have to do. I mean, I had to fight just to get teams to happen so that we could let, people come in 3 at a time and do that type of thing.
It was less about the challenge, but using the tools and the
Oh, anybody? Oh, sure. Oh, I haven't seen anyone doing, let's say, high school level, quantum algorithms yet. Okay, I'd love to. I see there's no reason not to. I mean, I've got a 9-year-old grandson who's programming on it, okay, but that's thanks to me, Well, he also plays Destiny, but we won't talk about that. So, yes, I have no problem. This is something that they wrap their heads around really fast. It's not hard, it seems. Yeah. Yeah. Oh, no, I'd love to see that. And again, we're very supportive of putting stuff up on the site for others to use. So if you come up with anything or there's anything you guys would like to distribute more widely, Microsoft will be happy to support that. And we can also help out sometimes monetarily. We can help with materials. There's all sorts of things that are possible. Just get a hold of me. That's the easiest. Okay. Thank you very much.